Okay, so are there any questions so far? By the way, I think it's working, but I am able to record the lectures and make them available. And so maybe some of you have discovered that, but in case you haven't, if you go over to, oops, wrong app. If you go over to the McGraw-Hill, so if you sort of scroll down, there's this thing that says go to lectures. So you could do that. Or if you happen to explore library, it also has this lectures hotspot. And either way that you go, you'll get to the same place. And I think I can get them up there. Seems that I can actually get them up there. So if you need to go back and... sorry? Yes.
Is the screen recording or is it also voice?
It's voice and screen. Okay. And they kind of have these... I think the processing tries to see when you kind of skip from, it's supposed to be for like PowerPoint. Like if you switch to PowerPoint slide, then it kind of has a different place, so you don't have to watch the whole thing. You might be able to jump to a particular section. Okay. Okay. Let's see. So today, then, we want to pick up from what we were doing last time. And last time we were looking at this example of a multiple choice question with 5 choices. And then there's some new information. And what's the effect of the new? And the new information allows you to eliminate 2 choices. And so you kind of intuitively know, what the effect of that is. But then how can you sort of prove it using the math framework? Okay, and so this is from the book, following the book pretty much, and maybe we'll say a little bit about TVM, maybe not. Okay, so last time we were looking at a issue of what's the probability the answer choice A is correct. And the first step is, what's the sample space? Okay, and so how do we analyze this? All right, and so keep in mind, right, that what we want. So in the back of your mind, what framework are we trying to use? We're going to try to use this conditional probability framework. Okay, and so for conditional probability, we need basically the 2 events, like a main event and some other event. Okay, so, and then we're going to, I guess some people would say we're going to condition on the other event. And so where it's the new information, so how do we represent the new information? Okay, so this is kind of where we want to go, sort of our vision, where we would like to end up. And so how do we get there, right? So we have to have some type of a representation for our sample space, or our events, sample space and events. So how do we represent an event? And so here, let's use a notation where the uppercase letter will mean that the answer choice is true, and the lowercase letter means that those answer choices are false. So we'll say there's only 5 events, okay? And if event A is true, then the others are false, right? So the others are lowercase. If event B, right, so uppercase means B is true. So if B is true, then the others are all false, right, or incorrect, right, and so forth. Okay, so this is our sample. These are our events, base events. Okay, so now we need to define some sort of events or compound events for us to fit into the contingency table, right? And so we'll let one event be that A is true, so that's kind of a simple event. And then the complement of that, the sort of remaining events in the sample space that are not the one where A is true, are all the others, right? So that one's easy. So the new information that we have is that choices D and E are false. Okay, and so if choices D and E are false, well, that means that it could be A is true, could be B is true, or could be C is true. Okay, and so we'll say that because it's a little bit tricky because we kind of want to set it up this way. So the opposite of D and E being incorrect, being false, are that possibly D and possibly E are correct. Okay, so that's the complement. Okay, so these are basically our two, this is our A set where A is correct, and then D and E are not correct, which is really the same as saying that A, B, and C are correct. Okay, and so then our complements are the rest of the sample space that's, not this one, and so the bar is not this one. Okay, and so what's probability, right? It's the number of cases where, or events where you have divided by the sample space, and so clearly that's 1 out of 5 at the beginning with no information, no new information. Okay, so now that we have the additional information, D and E are incorrect, we know that you have a 1 in 3. You know that your chances are higher, right? So how do you show that, right? And so here we want to say, what's the probability that A is correct, given now that D and E are not correct? Okay, so how can we show that this probability is 1/3, right? And so we fill in the contingency table, right? So here's a part where A and DE are true, and here's a part where A and not DE are true, right? And so how could A be correct and D and E be correct? That's not possible. Okay, and then the intersection where A is correct and D and E are incorrect, there's only this one case. Okay, and then the opposite, sort of the complement, the A complement of that, and D and E are not correct, are where B and C are true, basically, right? So here's D and E are not correct, and B and C are true. Okay, and then the last case where basically D and E are correct and not A. So this is the entire not A set. So, right? And so the entire A set is here, and the entire not A set is here, and then the entire cases, all the cases where D and E are incorrect are here, and then the complement of those are basically over here. Okay, and so if we wanted to use the Venn diagram, this is what it would look like. So the A set is here, and so it only has an intersection with the DE set, right? And then outside DE would be down here. Okay, and so last time we basically applied. Oh, and then there's this formula for conditional probability where you just take the probability of A intersect what it is conditioned on, right? And then you divide by this probability of the condition set. Okay, and so the DE, what's the probability of DE? That will be this 3/5. And notice that this is sort of the new reality, right? If D and E are incorrect, our new reality is it could be A, it could be B, or it could be C, right? So this is our new reality, and so we're dividing by our new reality, right? To divide by 3/5. But then when you, the reciprocal, dividing by a fraction is the same as multiplying by the reciprocal. So this is the reciprocal, right, of 3/5, 5/3. So then the 5s cancel, and so we have this new space. And so, you might think about, dividing by a fraction, right? So if you take 1, imagine you have 1 piece of pie, right? And you divided it in half, right? How many pieces do you have? You have 2, right? So you started it with 1 piece, the whole 1, and then now you have the 2. They're smaller, right? They're halves, but there's 2, right? Or divided into quarters, right? So you have 1 pie, right? And you divide it by a quarter, right? So how many pieces you have? You have 4. They're all little quarters. But you went from the 1, because you're dividing by a quarter, divided into quarters, you get 4, right? So the number increases, although the pieces are getting smaller, right? So that's basically what's going on. Okay. So this is the basic formula for the conditional probability, right? And what's the structure of that? How could you remember that? Why is that? Well, you could say that if what's the probability of E? And so, well, I guess if you look at something like this, right? The probability of you want to say a given that DE is true, and so in a certain sense, what you're doing is you're chopping off this part. It's like you're saying in a way goodbye to that part if you condition on it, and so those events are not possible. So you strike them out, and so what's happening is the sample size used to include those, used to be 5, but now that you can rule those events out, the sample space is smaller in size. It's reduced. Okay, that's what the new information does. So those are no longer possible. So you eliminate them, and so the sample space gets smaller. And so the new possibility has to be where A is true and the new event has got to be true. So the possible cases are here, and that could help you remember the formula. So if the information is that F has occurred and not F is ruled out, right, then the probability that E has happened, we're given that this has happened, right? And so this part of A is ruled out, right? And this is the part of A that must have happened in this new sample space, right? In this new sample space, okay? And so that's why dividing by the sample space kind of makes sense. Okay, so we'll continue with one more example, right? So let's suppose that you roll a fair die. What's the probability for an odd number? Okay, and then you have some new information that the roll is prime. And so what's the new probability? Okay, so how would we do this? Where do you begin? With something about odd numbers?
Yeah, so 1 through 6, all the odd numbers, so 1 through 5.
1 through 5, right. So you want to have something, and so what would you call those odd numbers? You might call them, or think of a letter. O. So that's actually not a bad choice, except, well, the problem with O is that it could be confused with 0. And so sometimes people put like an inside mark to say that it's 0, as opposed to, right, this sort of slash, which is the null set or empty set. So sometimes, because of the confusion, it's better to avoid O. So maybe D, right? So the second set, so it's a second letter, right? So how about you might say let, or you might, following the Microsoft Excel convention, whatever is in bracket is optional. So you might say let, or you might just avoid it. You might say that D is equal to 1, 3, 5. And then, you might make a comment to yourself, odd. Right? So at minimum, you should have D equals 1, 3, 5. Right? And then, however verbose you want to be, that's up to you, right? So now we have the odd numbers. And so then what do we want? What is the probability for an odd number? We want P, right? Yeah. P of D is equal to what, right? That's basically what we want to do, right? And so how do we do that, right? Remember that the probability is, say, the number in D or in that set, those events, divided by the sample space, or omega, right? And so clearly, right, 1, 2, 3, right? 1, 3, 5, there's 3 of them, and then the sample space is 6, right? So it's 1/2 or 0.5. Okay, easy. Now we have some new information. The role is prime. What's the new probability? Prime. So prime numbers. You have to, the sort of the trick to remember is that 1 is not prime. Okay, 1 is not prime. So 2 is the smallest, and only what prime number? The only even. Okay, all the others are odd. Okay, so 2 is the smallest one, and it's the only even one. So P prime, right, P, so it could be probability, right? You know, like this P, so is it the probability P or is it set P? Yeah, so you kind of avoid, just similarly, right? Simply like avoiding O. So maybe the second one, R, right? So R is equal to 2, 3, 5 prime. And then you might underline R because that's why I chose prime. Could underline D if you want, but depends on how clear you want to communicate stuff. If it's just for yourself, but anyway. Okay? So you kind of can spot the answer, right? So what do we want, right? The new information, so what's the new probability? So what we're really looking for is we're looking for a probability, right? So we want P, right? We want this P of R, right? No, sorry. We want the P of D, because that's our main thing. What's the probability that is odd? So what's the probability that it's odd? And then with the new information, how do you incorporate the new information, right? So that's given that it's prime. So this is what we want to figure out, right? So here's, so you sometimes, there's so many things that you can calculate. You have to make sure, what am I really looking for? So we want this one. So this is the total probability, the full probability, unconditioned probability. And now there's new information, given this vertical bar, given that it's prime. So if this is our new sample space, what's the probability that it's odd, right? Clearly, this is odd, and this is odd. So it's really 2 out of 3, which is about 0.67, say, right? So that's, in this case, you can just spot it. But the question is, how could we show it? How could we compute it? How can we prove it? So what should we use? You know, it's like if you want to do like a wood project, you know, what do? You go to the wood shop and you have, you know, your table saws, and maybe you have a circular saw, or you've got some drill presses and a bunch of screws and nails lying around, maybe hammers and screwdrivers, right? You want to go to the workshop, right, where you have all the tools, right? And so when you want to solve a math problem, solve a probability problem, statistics problem, what do, right? You have to use your tool set. You have to use your frameworks, right, to help you. And so, you know, like the cost CVP framework, you know, the variable cost, fixed cost, right, the TVM framework, those three and quote-unquote environment ones, compounding, interest rate, the number of periods, right, and then the cash flows. Those are your tools to help you answer these kinds of problems. In this case, what tools should we use? Just don't close that. Well, I don't want you to draw it out. I think that you should draw it out, right? That's the idea, right? That's the idea. And so, what do you draw it out into? Contingency table, right? Yeah, you should use a contingency table, or you could choose the Venn diagram. I think the Venn diagram is, you know, more helpful to look at inclusion, what's in and what's not in. When you want to do these kinds of conditional probability problems, I think it's more helpful to have the contingency table, right? And so, you know, it doesn't really matter which ones you put on this side or this side. You know, there's a transpose where you just sort of flip x to y, or you just sort of flip, and so it really doesn't matter. One of the, you know, conventions, though, right, is that you're gonna say strike out this side, so, and this side becomes the new reality, right? And so if you follow that convention, then this is R prime, right? And this would be not prime, and then this is this. These are the events that you're going to strike out, and the new sample space will be this instead of the whole thing. But if you want to do it the other way, then you would be striking out this one, and this is your new reality. That's fine. So it doesn't really matter. But here, so we have the odd ones, and that would be not odd. So then what do we do? Your life, when you want to fill in the contingency table, your life is a lot easier if you start where? Starting at the intersection is easiest, right? So that would be right there, right? In the Venn diagram, right? The intersection, the middle, is the same as this first box over here. So either think mentally of starting in the middle of the Venn diagram, and then you just have to remember that this is actually the intersection. That corresponds to the middle of the Venn diagram, the intersection. So what's in the intersection? Three and 5, right? 3 and 5 are in the intersection. So you might say 3, 5. So then odd, right? 3, 5, right? So what is in D but is not prime will be 1. Okay, because it's odd, but it's not prime. Okay, continuing vertically, right? The prime numbers, right? So what's a prime number? So it is prime, but it's not in D. It's not odd. What prime number is not odd? 2, right? 2. Okay. So then we can kind of go 1, 2, 3, 4, right? We're missing 4. 5 got over there, and we're missing number 6. Right? So these are not odd, right? Not odd, and they're not prime. Right? So they're not odd and they're not prime. Right? So you got those in the not D and not E section. So you can kind of check. Right? So that's sort of filling it out. D and not D, right? We have 2 over here and 1 over there, and then we have 1 over there, and we have 2 over there, right? And so here there's 3 primes, 3 non-primes, there's 3 odds, 3 not odds, and then our sort of grand total is 6. Okay, and so you can use the contingency table because to just spot the probability, right? So you could look at it and say, okay, if R is not possible and these cases are now gone, these events are now gone, then the probability that it's odd, given that the probability that it's odd, given that it's prime, it's really 2 out of 3. So you can actually see it from the contingency table. You can spot it, right? But if we wanted to use that formula, right, we would say that P, the probability of D given R, is the probability of D and R divided by the probability of R. So we want to basically convert the sample space to the smaller sample space, right? So what's the probability of D and R? So the probability of D and R would be this total probability, right? So it would be 2 out of 6. Okay, so for this cell in the big table, it would be 2 out of 6. Okay, and the probability of R itself would be 3 out of 6, right? This is the R set. R is this 2, 3, 5 out of 6, right? So that'd be 3 out of 6. So when you compute that, you do 2 out of 6 times the reciprocal, right? So 2 out of 6 is right there, numerator, and then when you want to multiply by something that's in the denominator, if you have a denominator problem, you can multiply by the reciprocal. So that's the reciprocal. So then the old sample space goes away, and we have the new one. And so that's how we show that, or use the conditional probability formula to show that it's 2/3. Does that make sense? Yeah? Okay, so now we want to continue this type of analysis, but we want to look at another type of a situation, basically, right? So let's look at 2 tosses of a fair coin. Okay, so we're going to toss a fair coin twice. And we want to know first, what's the probability that the second toss is ahead, given that the first toss is also ahead? Okay? So how do we start? And what's our framework, or what's the model that we're going to try to do? So 2 tosses of a fair coin, and we want to know the probability that the second toss is ahead, given that the first is also ahead. So what kind of a problem is this? This is it's a probability problem, yeah? So we're using that stuff. And it's given that something, right? So not only is it a probability problem, it's one of those like conditional probability problems, right? So what is the probability that the second toss is ahead, given that the first is also ahead, right? So basically we want the probability, right? Probability that, and then given something, right? So, what are we asking? What do we need to look for, right? So we just basically translate it, right? What is the probability that the second toss is ahead, given that the first is also ahead? Right, so something about number 2 is head, right? Given that the first is also head, given that number 1 is head. Oops, it's a little bit sad, in English classes, right? They tell you to use all of these adjectives that describe all of these things, right? And then in math, it's like you have a lot of extra stuff is kind of confusing in a way, and you want to just abstract everything. You want to simplify everything. So like a lot of embellishments, you just sort of throw away, and you need to do that if you want to concentrate on what's important, right? And so when you kind of reduce things to symbols, right? So instead of saying the odd numbers, we just say D, right? And instead of saying the ones that are not odd, we just say D bar, right? And instead of saying the prime ones like 2, 3, 5, we just do R, right? And the ones that are not, just R bar, So it's very, very abstract. It's very distilled in a way. But the advantage of that is that it helps you to concentrate on what is important. What do I need to focus on? Okay, and so that's part of, I guess, analysis, right? So also ahead, it's not there, given that the first one is ahead. Right, so you kind of, if you do this stuff, you kind of try to you get in the habit of finding what's not relevant and what is relevant, and then whatever is relevant, well, let's isolate those and think about those and what do those mean? Okay. So what should we do next? Make some kind of a table. What kind of a table? There's lots of kinds of tables. You want to kind of know what you're dealing with, right? So what would help you know what you're dealing with if you could see what? See what? if you could see the sample space, that would really give you a lot of clarity, right? So what does a sample space look like? So we'll have, how big is the sample space? Size of the sample space. So something about 2. Okay, so we're doing this twice, right? So this is toss number 1. And then say, right? And then we're going to do toss number 2. So when we toss the first time, what are the possible, how many possible outcomes are there? 2, right? Heads or tails. And when we do it the second time, it's the same thing, right? So 2 times 2 is 4. Okay, so we should be looking for a sample space with size 4. We should be looking for 4 events. Okay, so if you've done this for a while, it kind of becomes old hat. But the convention, and you don't have to do it this way, but it's to flip the one on the right. So the one on the right is heads, tails, right? Because it's just the one on the right. And then you sort of freeze the one, the one in. So the one in from the right, you sort of freeze until you run out of those possibilities. Okay. Then you flip that one, and then anyway. So if this, for example, had 3 possibilities, we would do like A, B, C, and this would be like capital A, capital A, capital A, and then capital B, and then capital C, or something like that, right? So you you kind of cycle through all of them on the right, and then if we're doing 3 tosses of a coin, we would have say this would be H, and then we would have a T, and then we would basically just repeat this block down here. And then if we did 4 tosses of a coin, we would have, basically this block like repeated here, and then repeated here, and then repeated there, and then it would just be bigger and bigger and bigger. Okay, but usually you flip that right one on the right through, you cycle through its total, all of its possibilities, and then you repeat cycling it through, and then one end you do it, this, and then so forth. Okay, that's usually what people do, but as long it doesn't really matter, as long as you got all of them. Okay, so that's our sample space. Two tosses of a coin. Okay, so that actually helps, I think, because now we know, or at least we know, we're dealing with something size 4, right? And we can see them. We can see everything. So it gives us visibility. It gives us some clarity, right? So what should we do next? So that was helpful. I think that's a good way to begin, right? What am I dealing with? If you can, see the sample space, or if the sample space is too big, you might say, well, I don't want to do all of them, but let me just do a few, because if I just look at the first, 5 or so, 6, then maybe that'll give me some help seeing what the set looks like, what the sample space looks like. Okay, here we can do all of them, right? But and so I think it's helpful to look at least the first few. In this case, there's so few that we can get all of them. So what's next? when you think again of these conditional probabilities, what's might give you a window into seeing what's going on? The contingency table, right? It kind of looks like a little bit like a window, right? So what would be your parts, right? So here, this is the one that you want to sort of go away, right? And this is the one that you want to concentrate on, right? So you might say H1, say, and then not H1 or the complement of H1, right? Because this is the one, so what is probably that the second one is ahead, given that the first one is ahead. So given that the first one is ahead, this is the excess part of the sample space that we're going to chop off by saying the first one was ahead. Okay, but now we want to look at the whole thing. So if this is the vertical one, then this one would become the horizontal one, say, and we'll be saying that H1 basically is that the first one is ahead, right? And then H2 would be so that would be the first one would be ahead there, and H2 would be the second one is ahead. So this one would be ahead, and that one would be ahead. Right. So in our sample space of 4, where the first one is ahead, that occurs twice, and where the second one is ahead, that one occurs twice also. Like there, case 1 and case 3. Okay. So the window is, or the contingency table is looking kind of empty, right? Should fill it in. So best place to start is the intersection, right? This upper left corner, right? That will be the intersection in the Venn diagram. So where is the first one head and the second one head, right? So that would be H, H. That will be this case 1, right? And so continuing, right? H1. So the other H2, the other H2 would be this one, right? And so this one would be tails head, and that's where the first one is not ahead, and the second one is ahead. So that there it is right there. Okay. So the H1 then, H1 is here. So here H1 is ahead. Also H2 is ahead. Here we're looking for the case where H1 is ahead, and then H2 is not head, so that's tails. And then clearly, if the first one is not heads, tails, and the second one is not heads, then it's also tails. Okay, so then we should have our one with the numbers, H1, not H1, H2, not H2, a complement of H2. So it turns out that there's just 1 in each one. So there's 2, 2, and then here's our 4, and 2, and 2, and that gives us our total expected cases. Right. So you might ask, what's the probability of H2, right? What's the probability that the second one is ahead, right? So that would be this case and this case, right? But you can see that you can get it off of the contingency table by, here's the set H2, so that would be 2 over 4. 2 over 4, so that's equal to a half, which is equal to 0.5. Right? But what we really want is what's the probability that the second one is ahead given that the first one is ahead, right? So what we really want is the probability that that the second one is ahead given that the first one was ahead, right? So that's a probability of, I'll just flip them around. H2 and H1 is the same as H1 and H2. So technically, I mean, I might want to have H2 and then and H1, but they're the same, right? So I'll just flip them around. And then this is the probability of H1. Right? So what's the probability of H1 and H2? That will be here. That's the intersection of H1 and H2 over 4. So this would be 1 over 4. So what's the probability that the first one's ahead and the second one's ahead? 1 out of 4, right? 1 out of 4. And then what's the probability of H1? So H1 is really 2 out of 4. 2 out of 4. So here's the numerator, right? And then I'm going to do the reciprocal to the denominator, right? When I divide by a fraction, I can multiply by the reciprocal, and so I get a half, which is equal to 0.5. And so what do you notice? Notice the probability of H2 is equal to the probability of H2 given H1. Right. So if we look back, right, the probability, of that it's odd is a half. Right, 3 out of 6. Right. But the probability of D, given the new information, changed. It changed from 1/2 to 2/3, right, which is about equal to 0.67. I should say approximately equal to 0.67. Right, so it started at 0.5 and then it got larger to 0.67, but it changed. Right, the new information changed the probability. Here, in this case, the new information did not change the probability. It's still the same, half, right? And so that's kind of a special case, and we call that independent. Okay, it's independent. The probabilities are independent. Okay. Similarly, if we toss a fair coin 3 times, right? So here, it's nice to see the sample space. It's kind of tedious to draw the whole thing up, but again, you can see this convention. On the right, you go heads, tails. You exhaust the possibilities: heads, tails, heads, tails, heads, tails, heads, tails, and then one in from that. Here in the middle column, you do heads, heads, tails, tails, heads, heads, tails, tails. So you kind of repeat that pattern, and then to the left of that, on that, all the way to the left, you have heads, 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 and then tails, tails, tails. Okay, and then you get all of them. And oh, by the way, we know there's 8, right? How could you sort of prove that there's 8, or how many size? Right? You could say this is the first roll or toss. This is the second toss. This is the third toss. How many possibilities? Well, 2, right? Just like before, heads or tails, and so just like up above. And then now we flip another coin. Well, there's just 2 more, right? So you multiply those together, and so you get 8. So this is how many you expect to have. Okay, so this is like, in the first case, there's 2 possibilities. The second case, there's also 2 possibilities. The third case, there's also 2 possibilities, and so we have 8. Okay? And so given that the first 2 tosses are heads, what is the probability that the third toss is also heads? What do you think? A lot of people will say, oh, it's 1/8. And that's actually, because there are 8 possibilities and 3 heads in a row is, there's only one case where you have 3 heads in a row and there's 1 out of 8. Okay, so that's asking, probability that you have, I guess, H is equal to 1/8. Okay, that's not what we're asking, right? What we're asking is, given that the first 2 tosses were heads, right? So, when you read these things in English, it's kind of backwards, right? So, given that the first 2 tosses were heads. So, given that the first 2 tosses were heads, right? What is the probability that the third toss is? And so again, you can sort of drop off also. What is the probability that the third toss is heads, right? So we want, what's the probability of H3? Okay, this is different, right? Here, it's what's the probability of 3 heads in a row? Basically, this is probability of 3H in a row, in 3 tosses, right? So probability of 3 heads, that's 1/8. That's 1/8, right? Sample size. How many cases are there like that? There's only 1. What's the sample size? 8. So there's 1 over 8. But this is a different question. It's given that we tossed 2 already. When we toss it the next time, what's the probability of heads or tails? Right? Anyone want to take a guess? So that's why we should do it out, right? Because we want to really, really convince ourselves that we got it right. Yeah? So what we want to do is we want to get a window, get some visibility onto this, right? So we look at our contingency table, right? And so just following the convention that this is the one that we want to get rid of, we have or condition on, or we're going to keep, and then we want to get rid of its complement. So and the one that we're interested in is H, that the third one is heads versus the third one's being tails, right? So the first you have heads on the first 2, and you also have heads, right? So where is it where you have heads in first one? Right? This is I'll just write it out, right? So here it's just H, right? And so not heads in 1 and 2, and the third one is heads, right? That would be this one, and this one, and this one, actually, right? Because here it's the third one is heads, 2, 3, right? So H3 would be the H3, right? Where is it that the third one is heads, right? So the third one is heads over there, the third one is heads over there, the third one is heads over there, and the third one is heads over there. So those are the 4 cases where we have the third one is heads. Okay, so not heads for 1 and 2. So that's here, right? Because there's number 1 is heads, but number 2 is tails. So we actually include that, right? So that would be the HTH. And then this other one would be the THH. And then the last one would be this TTH. TTH. Right? Because here, the third one is heads. Okay? And the first two, number 1 and number 2 are not heads. So here we got tails in number 2, here we got tails in number 1, and here we got the 2 tails. So that actually is H3. Right? So H3 has all 4, is of size 4, right? So here, this one is heads in 1 and 2, right? And then the third one is not heads. Right, so where do we have the heads being 1 and 2, where you have heads in 1 and heads in 2, and not heads in 3, right? That's actually only this one, right? Because this one is actually HH. So the first 2 are heads in a row, but the third one is tails. Okay, so this one has 2. Okay, so we got all 2 of them. We got both of them, I guess. And then this one, for this one should have the remaining 3. Oh yeah, so there should be 3 in here. Okay, so then if we have 3 in here, then this would give us 4, and then this would give us 6, and they would add up to 8, right? So we're looking for 3 over here, right? So it's actually probably exactly these, but the last one is tails, right? So it's probably HTT, THT, and then TTT. Right, so then this would give us 2, and this would give us 6, and so the sum of 2 plus 6 is 8. Then here across this is 4, here across this is 4, and 4 plus 4 is 8. Okay, so our contingency table that we're going to use, right, is 1, 3, 1, 3. So it's H12, and then complement of H12, and then H3, and complement of H3. And so again, this is 4, 4, and 8, and this is 2, and 6, and 8. Yeah. Okay, so probability of H3 given H12, right? Probability of H3, right, I think is 4 out of 8. Oh yeah, so the probability that, right, so that's equal to the probability of H3 over the probability, intersection, probability of H12 intersect H3 divided by the probability of H12, right? So when we have the conditional probability, right, the numerator is the intersection, and the denominator is what you are conditioned on. Okay? So this intersection, right, it's here, right? So it's this one, intersection 1 out of 8, and then the probability of H12 is this half over here, or it's 2, sorry, no, it's not half, 2 out of 8, 2 out of 8. So when I multiply, I just copy the numerator over, and then I take the reciprocal of the denominator. And so that's equal to 1/2, which is 0.5. Does that make sense? So this is independent. Right? Because, oh, well, yeah, the probability of H3 by itself, probably see the probability of H3 by itself is equal to 4 out of 8, which is equal to 1/2, which is equal to 0.5, right? So probability of H3 equals the probability of H3 given that the first two were heads. So the history, what happened before, doesn't matter. If the question is, what's the next flip going to be, heads or tails, it's a 50-50 chance. So every time you flip a coin, the next flip, there's always a 50-50 chance. If you're just looking at, what's the probability of heads or tails on the next flip. That's different from looking at the whole history. Does that make sense? Okay. So that's what we've shown, right? And so here's sort of a recap, the Venn diagram visual with the contingency table, right? And then also with the 3 flips, right? And so what we want to keep in mind is this idea about independence, right? So event E is defined as independent if the conditional, if the new information does not change the probability. Okay, and so if E is independent of F, then F is also independent of E. And so this is just sort of a proof of that. So we want to prove that F is independent, that F given E is equal to the probability, sorry, this should be of F. Right, the probability of F given E is the probability of F. Okay, so here you want to start with the probability of F given E, and what you want to end up with is the probability of F, right? So by the definition, right, this is E and F divided by the probability of E. So E and F is you can multiply by F, right? And so but probability of E given F is the same. It's independent. So you're given. So E is independent of F. So here's where you use that E is independent of F. So probability of E given F is equal to the probability of E. So this is where you use the independence. Okay, then you can cancel the probability of E, and so you get the probability of F. So now you've shown that if the probability of E given F is the same as E, that they're independent, then it works the other way around. Okay, and so the important takeaway is that right, this probability of E and F. So if you start here, you can get this one. Okay, so the probability of E and F equals the probability of sorry, so you start here. Anyway, they're all basically the same, right? So E given F, and so what you want to do is you want to convince yourself that if they're independent, to get the and the intersection probability, you can just multiply them. You don't have to condition on anything, right? So you can check the probability of all heads is equal to the probability of H1, 2, and H3. So the probability of that times the probability of that. So 2 out of 8 times 4 over 8, right, actually gives 1/8. Okay, so remember, let's see, yeah, right. So remember, if you have like the probability of, say, A union B, right, that's actually equal to the probability of A, basically plus the probability of B, and then you have to subtract with this probability of A intersect B, but there may be a case where it's 0. In that case, mutually exclusive, right? Mutually exclusive. Okay, so if it's mutually exclusive, then you can just add the probabilities. Okay, so in general, for intersection, you have to multiply by the conditional probability, but if they're independent, you can just multiply. So independent probability of, say, A intersect B is just equal to the probability of A times the probability of B. You don't have to have the conditional if you know that they're independent. Again, remember, or when you take these probabilities, you get more probability. But the intersection is you're just carving out a little bit of this one, you're carving out a little bit of this one, and so this combined probability is smaller. You would expect the probability to be smaller than this one and smaller than that one. And so clearly you take, two fractions, you multiply them, you get something smaller. Right, so this would be larger. Okay. So let's see if we can maybe so this would just be another example, kind of along the lines of the others that we've done, and you want to ask, is advertising effective? So basically, the question is advertising effective? Or is advertising worth it? Okay. And so if we go through this example, the bottom line is, we would define, like S, no, because that sounds like the sample set. We'd be A equals, say, saw the advertisement. Okay, and we would have, say, B, say, instead of purchase, which sounds like P, but it sounds like probability, we use B for bought the product. Okay, and so basically you want to examine, what do you want to examine? The total probability that they bought versus the probability that they bought given that they saw the ad. Does that make sense? So this is what's the general behavior of people of buying this product. General behavior of buying this product. And then what's the behavior of people who buy the product given that they saw the ad? Right? Given that they saw the ad. Because if this, what? So if PB equals PB given A, then what? Independent. On the other hand, if PB is what you hope is less than PB given A, then what? not independent. So if your general probability of people buying, this would be that they're unaffected by the ad, right? Like they saw the ad and it didn't change anything. So if it's independent, that means that what? Right? If it's independent, right? It means that there was no effect. Right? Whereas if there's a general likelihood to buy this product. However, of the ones who saw the ad, the probability of buying the product increased. Then what? Ad was effective. Right? So you have to find out if people, measure some way of did people see the ad, who saw the ad, who didn't see the ad, right? And then you could use this idea of independence to find out if the ad was effective or not. Does that make sense? So you use this concept of if you actually do this as an exercise, you should find out yes, it was they're basically not independent. Okay. Now, I want to make sure that you understand that this contingency table really distills a lot of information. It really contains so much information, right? And so here, what this page is trying to show you that sometimes we're asking about questions about the whole population, and so we could be certain groups, parts of it, and so in that case you always divide by this sort of grand total out here. So what's the probability of A? What's the probability of B? Right? So if you're asking about sort of total or whole probabilities, the contingency table, sort of runs as an entire table, and this is your denominator. Okay. On the other hand, okay, sometimes, you want to ask specific questions about B, right, or its complement, or questions about here. Given B, right, basically means that you strike out this set, right, and that this set did not happen, and so then the new sample space is 6. So then your denominator shifts to being the row denominator. Okay, or sometimes you may, well, what if this was ruled out, and then you have this one, and then in that case you use the row sum basically as the denominator. Okay, and so I'm kind of trying to gray this out here so that it's not important. Here, sometimes you use the column sum, and so here this is grayed out, right? So now this is not important. And then here both denominators are 5, and so we're using just this column contingent probability. Okay, so the contingency table actually packs a lot of, or there's so many different questions that you can answer from the contingency table. So just be aware that if the question is about the population in total, then your denominator, this is your sample space, right? 10, the whole kit and caboodle, the whole thing. Sometimes if you're restricting yourself to that only B happened, or only that for some reason not B happened, there was an accident and everything was flipped around, not B, then your probabilities are based off of the row. And sometimes your probabilities are based off on the whole, right? So here, you can get the probability of A itself, so then you're using this 5 over 10, or the probability of not A. Okay, the probability of B is this 6, because that's a whole, all of B, the total B over the sample space, the total not B, complement of B over the sample space, right? So sometimes you're using this as your base, and some other times you're using the row sum as the denominator base, or sometimes the column sum as your denominator base. Okay, and then here it's just some examples of how you go from raw data to a contingency table. And so the way to do that is through this Excel transformation called the pivot table, and then you can actually get so then you would copy that, yeah. Okay, and so there's just, if you want to just skim through a quick review of some topics on TVM, that's there. Okay, all right, so that's it for today, and we'll see you tomorrow.